Okay, so after this very nice introduction that I always love to put to start, I don't know if you find it too burdensome, but I think it puts a nice touch when you are looking at them in the YouTube. Anyway, let's go to our lessons. What have we seen till today or till last day? First, we saw two different ways to calculate the gain of an amplifier. As you remember, first we can calculate the wall transfer function and then calculate the derivative at the quiescent point. That's it. So we get this as this derivative here, which is the slope, which means that at this point the gain is just this derivative. But we saw that calculating this function is, in the general case, very complex, so it's not a very good idea. The second way we saw was calculating only the quiescent point using the large signal model, and then rewrite the circuit using the small signal model. Okay, and then calculate everything from there using the small signal model, which means using a very small signal overimposed on a large signal which is quiescent. Okay, yeah, remember? Tell me yes. If it's yes, raise your hands. If it's not, raise your hands. Is there anybody there? Okay, thank you. Otherwise, for me, it's complex working without feedback. Okay, you're having big day. Bumper fit. Okay, just we replace the large signal by the small signal, and we go on from that. But we saw that that was only for low frequencies. For high frequencies, what we did was forgetting about this model and improve it by using the different capacitances. We saw also the Miller theorem that causes the gain to be affected very importantly, very strongly by the feedback capacitance between gate and drain, or gate and source, or whatever, depending on the configuration. And that was an important effect when we were looking at the basic building blocks for basic amplifiers, that are these three, that are the common source, the common gate, and the common drain. Okay? Usually the one we use is the common source, but the other two also can have some applications. Okay, we revisited the common source amplifier, and we found that okay, it's a very nice amplifier, very easy. And we also introduced the cascode amplifier. The cascode amplifier is just a common source amplifier with a common gate on top. Okay, you remember? You see, just we add the common gate amplifier is just M1, and we add another common gate amplifier which is M2. Okay, and it has some very nice advantages. Okay, for instance, in the common source, the gain is proportional to the gain of the transistor. You can multiply it by the resistance, by the output resistance. Okay, so for very large loads, this is just the maximum gain is Gm, which is the transconductance of the transistor multiplied by the output resistance. Okay, but this is very, very small. It can be 20, 50, 100 at most, if you remember when we were talking about that. Instead, the cascode amplifier has a much higher gain, which goes like that, which is GM-R0, which is the maximum gain of the single amplifier, multiplied by the gain by itself again. So if this basic feature, if this basic number is maybe 50, 20, we get gains that are in the order of the hundreds or even thousands, which is much higher. Okay. And another nice feature of this amplifier, of this kind of configuration, is that the gate to drain capacitance in M1 is not amplified by the Miller theorem, because the gain there is more or less 1. So it's a very small gain. Thus, the input capacitance for the cascode is much smaller, much lower than in the common source, meaning that the input impedance of the cascode amplifier is much higher than the input impedance of the common source, which is good because it helps improving the performance of the amplifier. But remember, you see that? This is just by applying Kirchhoff's law at this node. Okay? So the basic idea is that if you increase this current, if you increase one of the currents, this current, for instance, the other one will go down. Okay? So you get here, automatically, you get this differential amplification, or this differential behavior in the currents. Okay? Yeah? Can you see the idea? It's very straightforward and very clever. You notice that, for instance, here, when you look at the inputs for volt, or for when both inputs are equal, we should have exactly the same current. Okay? For equal inputs, we should have that the currents are equal at the output. Okay? This is the idea about the differential pair. So that should make no difference. The level of the input should make no difference. What makes difference, we care only about the difference of the applied voltages. Okay, we care only about the difference between V plus and V minus. Okay, this is what we call the differential signal. The I is input and D is differential here in this signal. VID means the differential voltage at the input, and is defined just as V plus minus V minus. Okay, it's kind of the idea of the small signal. It's not the small signal, but it's very similar. Okay, it's just the difference between two signals, and then from this point of view, it makes no difference that if they are both at 1, 2, or 3, or 4 volts, because the difference, the important value is always the difference between them. Okay? Yes? And when we have here an ideal current source, this is what it is. Okay? It's not important the absolute value. The only thing important is the difference of value. In the real case, it is important. Okay, because in the actual case, we still need a second variable that describes the actual value of the voltage with respect to ground. Okay, because otherwise there is something missing. In fact, we are making a change of variables from V plus and V minus to two other different variables. Okay. And you know that if we have two values, we can map them to other two values. Okay, we cannot map to 1 or to 3 being independent. This is basic mathematics. We could choose either V plus or V minus as the reference voltage. But since we are nerds, I'm sorry, but you are studying the 4th course of electronics, of engineering, so you qualify to be slightly nerd. We are looking for a more elegant solution, which is defining the common mode voltage. What's the common mode voltage? we define the common mode voltage as this. Okay, the average of the inputs. Okay, and the differential is just the difference between the inputs. Okay, so using these two definitions, it's very easy to see that the input B plus equals the common mode voltage plus 1/2 of the differential voltage. B minus is the same level of reference, which is the common mode, minus 1/2 of the differential voltage. Okay? Yeah. Questions? Is there any question? Is there any question? No? Okay. Then using this kind of signals is good because, for instance, we cannot solve the bias issue. Okay, we not only we solve the bias issue, but we are also mitigating some problems that come when you are using single-ended signals. For instance, assume that you are having a line with a signal that is referenced to ground and has some influence by whatever. For instance, the value of a high resistor that is affected by an external electromagnetic field, for instance, or two signals that are coupled through a capacitor, as are in microelectronic design. Okay, for instance, so when you are having a signal here that goes through the green line, but it's coupled to something like that, to another line that goes over, for instance, or below, which is another layer, and you have a signal in this aggressor, they can be coupled through a capacitor. If you remember, capacitor for high voltage, for high frequency, it just is an impedance, so signals can go from one line to the other through this capacitor. Okay? This is called capacitive coupling, and it's a very big problem in integrated circuits. Okay, so in this case, even if the signal is constant in the green line at the beginning of the green line, at the end, because of this signal, of the aggressor signal, you will get some spurious signal at the output of the green line, which is bad because it can cause the system to malfunction. Okay, so this is a problem. And using single-ended signals is not easy to solve. But if we are using differential signaling, then most probably the signal in the aggressor will affect, if it's well designed, will affect similarly both of the signals. Okay? So at the end, we will have the same signal, the same shape, or a very similar shape at the output of both B plus and B minus. Okay? And in this case, what will change is only the common signal, not the differential. Okay, the differential signal, this one minus this one, sorry, is more or less constant. Is this one, this other. But the common mode voltage will show the effect of the aggressor. But since we are not worried about this common mode, and we are only worried about the differential, the signal is better. Okay? Understood? Yeah. Okay, this is one of the reasons to go for differential signals. This is useful when you're looking for small signals, small analog signals, or very fast signals. In fact, there are even some protocols, some communication protocols with high voltage that are using this kind of differential signaling. Okay, do you remember any of them? I'm quite sure that you have studied at least one of them. Do you remember? Can you remember some protocols, some communications protocol? No, but you have studied them, don't you? Now this is out of curiosity. Maybe. Do you remember, for instance, this? No? No? Oh. And this one? The serial communication port? No? And the CAN bus? The CAN bus? Yes? The CAN? Yes, yes, we can. Yeah, that's it. The CAN bus, for instance, uses differential signaling. Do you remember now? Okay, maybe yes or maybe not. But it's an example that you have already studied. And this is just to improve noise immunity. Because in a car, having noise immunity is a must. Okay, you cannot risk having some noise or some spurious signal affecting how all the security systems are working. So it has this kind of signaling, among other things. Okay, anyway, let's go back to the signal, to what we are doing, which is the sorry, the differential pair. Okay, let's go for the long channel equation, which is the most easy thing, the easiest thing. Okay, first we assume long channel equations, and as always, we assume that we are in saturation. Do you remember? Saturation means that the equation is going to be something like that. Okay? Yeah. Then, from this equation, we have this equation. We also have that the addition of both currents, the current flowing through both transistors, must add to I tail, to the current, to the bias tail, to the bias current, sorry, which is called I tail. Okay? And the differential current, we define it just as the difference between the two signals. Okay? That's easy. Then, using these definitions, these three definitions, these three equations, we get this equation. This equation is just solving for the current, the long channel equation, and this stands for both transistors. Okay, and then, if you wish, I can leave that for you for homework. We can also develop this function. We can also extract this function, which says that basically the current, the differential current is proportional to this function, which is the differential input here and here, the current and the gain. Okay? Yep. So this is the basic idea. Please try to do that at home. It can be important. Just to recover your hands. Okay, anyway, this expression is not elegant. Okay, and here we want to be as elegant as possible. Not just for the sake of elegance itself, but because an elegant expression is always much more easy to understand and gives you some nice insights on how the system is working. Okay, so the simpler the expression, the more elegant the expression, the more insight it can provide. Okay, this is philosophy, but it's some kind of philosophy that is very useful to explain explicitly. Otherwise, from time to time, it's just giving information and not explaining the motivation on why we are doing things, not how, because you are assumed to know how, but the why, which is more important. Okay, but we define this expression. Okay, and this expression is just saying that at the quiescent point, the current, notice, I tail, one half of I tail is just the current through one of the transistors equals one half of beta multiplied by the overlap voltage squared. And the overlap squared, this is just VGS minus VT squared. Okay, these two expressions are the same. Okay? Yeah. But this one looks much nicer. Okay, then using this expression, we can rewrite the previous expression, the previous equation, as this. Okay, which is nicer. But this is telling us that this depends on basically the relation between differential input and how long we are from the operation point. Okay, then this equation is predicting some things which are nice to look at. Okay, and easy to understand. Okay, notice that if the differential input is 0, then the output current is going to be 0. Okay, as expected. If there is no difference in the inputs, there has to be no difference at the outputs, neither in voltage or in current. Okay? Yeah. Easy to understand that. I mean, it's always depending on the definition of differential input. We want we want no difference at the output if there is no difference at the input. And this is exactly what this equation is telling us that we get with this kind of circuit. Yep. Okay. Then notice that the complete current steering takes place for some specific values of the input of the differential input. Okay. This is related to the quiescent point. The current steering means the relation between the output current and the bias current. Okay, so that means that the full current goes through one transistor or through the other transistor. Okay? Yeah? And this takes place at the moment where this relation between VID over the overlap voltage multiplied by this is plus or minus 1. Okay? Notice that we cannot have more current than that, I tail. Okay? And the question, and I would like you to, at least to answer, why this equation is not valid for input voltages over this voltage, this 1.4 overlap voltage. Why this equation goes to imaginary roots when we are going higher than this voltage? What is our mistake? Or which are the assumptions we are making that makes this equation not valid anymore for voltages higher than that? Any answer? Okay, let me show the picture. I love magic. Okay, the square is negative, yeah, but this is a consequence. This is not the reason. I mean, why? What in our equations is saying that we cannot go further than this? The answer, this is a song. The answer is written in the wind. The answer is that we are assuming that the transistors are in saturation. Okay? But when we go so further than the equation, this assumption is not valid anymore, the equations break. And by break, I mean we are going into the imaginary realm. Here, you can see it here at this equation. I mean, here in this equation, sorry, oops. You can see here in this curve, okay, it goes like that, like that, and goes down and like that. Okay, and our equation would be this line. Okay, but the actual equation is the actual behavior by simulation is the red line. Okay, and this is, do you remember the long channel transfer function? But it was doing something like that. And in this case, it's also similar. From this point and this point, our equations are actually not valid anymore because we are entering into the linear region or in the cutoff region, in the weak inversion region. So our assumption that we were using this equation is not valid anymore. So this equation stops being valid over these limits. Okay? Understood? So the equation is a good equation, but only when you are keeping inside the region where the equation is valid. Okay? Yeah? Okay. So let's consider the basic circuit. And let's consider the small signal analysis. Okay, the basic circuit is like that. It's just the small signal, sorry, the differential pair we were using, which is this one, and we add two very complex devices which are converting from current into voltage. Okay, and the most basic devices that can convert from current into voltage are resistors. Okay, so if a current is flowing through here and another current is flowing through here, then the output is going to be VCC minus I multiplied by R. Okay, so we are converting these changes in current caused by the changes of the transistors in changes into voltage caused by these resistors. Okay? Yeah. Assuming that the resistors are such that we are inside the dynamic range. That means that we are not going so far away that the voltage goes crazy, maybe that goes below the voltage necessary to keep them in the saturation range. Okay? Yeah. Okay. So, first of all, we will see how this is working in the small signal analysis. For that, we will find the equivalent transconductance by setting this point for each of the transistors. Okay, and at each transistor, we found that the transconductance is just the square root of beta multiplied by the current, and the output resistance is just 2 over lambda I tail. And this 2 is just caused by the definition of the tail current. Okay? Just remember how to calculate the small signal models from transistors. Okay? Please, from time to time, just randomly say yes or ah or okay or something like that, just to feel that I'm not talking to myself. Please, wait for me. Okay, thank you, thank you. Otherwise, it's called onanism. Just don't look for that on the internet. Or well, you can look for it. Okay, now let's do some magic, some tricks. This is quite, how to say that, the differential pair is a very nice circuit, but the tricks we can do with it in order to make the analysis are also lovely. I mean, they are so clever that will probably open your eyes to many other ideas in circuit analysis. Okay, so first of all, we want to calculate the differential gain. Okay, do you remember? You have studied operational amplifiers, don't you? I don't remember in which courses, but they told you that the gain was the differential gain multiplied by B plus minus B minus plus the gain in common mode multiplied by, okay, BCM. Okay, do you remember that? Or you were using only this first part and not with the common mode? It's just out of curiosity. You understand the idea of the common mode. Okay, but now, depending on the other side, yeah, okay, but the idea is that you know that the common mode exists. Okay, but let's see the differential gain. First of all, let's go for the differential gain. And as you know, the differential gain is defined as the relation between the differential output and the differential input when the common mode is 0. Okay? So in this case, when the common mode is 0, B plus is minus B minus. Okay, there is no common mode. So they are equal to 1/2 of the differential input. Okay, remember that the differential input is B plus minus B minus. Okay, so if they are equal, we get this expression. Okay, if the absolute value is the same, then this expression is valid. Okay, so when we are in these conditions, we don't need to work with this full circuit. Okay, we need to work only with 1/2 of the circuit. Why? You will tell me, how can we simplify that? We can simplify that because this is a virtual ground. Okay, that means that this is not 0, but it behaves as it were 0. Okay, and I can leave that for you to think. Okay, but just believe me that this is always 0. Just put the equations and you will see. Okay, independently of the values. So if this is always 0, we can go and just analyze one half of the circuit. Okay? Yeah? Yeah. Okay. And then this goes very easy to understand, because the small signal is just the small signal of a common source amplifier. Okay? Yes? So the gain is just the gain of the output resistance multiplied in parallel with the branch resistance. Okay, it's very easy to calculate. It's not even worth spending time on that. Okay? Yes? And then the other thing we want to calculate is the gain in the common mode. So this is something that can be calculated also. How do we do that? To do that, we do a clever trick. And the clever trick is saying that one resistor, like that, is absolutely equivalent to two resistors in parallel of value double value of 2R. Okay? So we just replace this resistor here by two resistors in parallel. Okay? Yeah, and in this case, we can also consider that there is no current flowing through this point, because they are exactly the same at each half of the circuit. Okay? So we need to analyze only one half of the circuit. Nice, isn't it? Notice that in this case, we are having this resistor. And in the other case, we didn't have it. We had a direct connection to ground. Okay? In this case, the small signal circuit is this one. Do you remember that using this configuration, we had having this resistance to ground between the source and ground reduced the gain but improved the stability of the system, because it was less independent on the gain. Okay, but in any case, the common mode gain can be calculated. In fact, it's easy to calculate as this one, as the gain that is put in the screen. Okay. So as you can see, it's when the tail resistance is very big. This goes simply to a combination between the gain and the output resistance. Okay, but the nice thing is calculating the gain in both cases just by adding this. Okay, just by dividing the circuit into, just because of the differential gain in this case, when there is no resistance to 0, and in this case just by using this trick of dividing one resistance into equal resistances. Okay, which is a very nice trick. Any questions? No? Okay. Then there are more relations that we need to have. Do you remember the common mode rejection ratio? it is just the relation between it's just the relation between the differential gain and the common mode gain. We want it to be infinite. We want it to be as high as possible. Okay, so in this case, for our case, when we are considering simply a resistively loaded differential pair and ignoring second order effects, with our output resistance, with the internal output resistance of the transistor being lower, much higher than the branch resistance, which is usually the case. I mean, the R at the branches can be 10 keys, 1 key, some keys, and the output resistance of the transistor can be 1 mega ohm. So it's quite a difference. Okay, so this is usually normal. Then you get that you can calculate the CMR, the common mode rejection ratio, and you do just the division, and you get this very simple expression that it's related to the gain of one transistor. Okay, and notice that this is not a very big value. Okay, it's not infinite. Okay, it's just R tail can be equivalent to the output resistance. So GM multiplied by the output resistance can be maybe 100. So this ratio, in this case, can be maybe 200, say, which is good. I mean, having the common mode gain 200 times less than the differential gain is good enough, but okay, it's not infinite. It's only 200 times, or 1000, or 100. Okay, but with this simple configuration, we get only to these values. Notice that if there is no output resistance, if this R tail goes to infinite, which means ignoring R tail, the CMR, the common mode rejection ratio, goes to infinite. Okay, but this is not usually the case. We will have a finite value of this R tail. Okay. Then other things to know are, for instance, the power supply rejection ratio, which is how the noise at the input affects the output of the signal. Sorry, the noise in the power supply affects the output of our system. And we define just these gains as the differential gain over the relation between the output signal and the volt and the noise, both at VCC and VSS, at the positive and negative power supplies, and we can get some expressions. However, it's preferred to have not expressions here, but at the input, something like that. So you can use this as a noise at the input, which is much powerful way of thinking of it. Okay, so you remember having done that in some other courses? Yes or not? Most probably you did that in instrumentation, or okay, but anyway. So, but do you understand the idea? So, okay, let me explain it slowly. You have a noise at both the positive power supply and the negative power supply. Okay? And you have these expressions that are just telling you how much the output is affected by this noise. Okay? So here, this is saying that the output is going to be, for instance, this VSS multiplied by the PS, PS. R over the gain. Okay? But then using this expression, sorry, the gain has to be here. And the P, sorry. What we are saying here is that the output is going to be this VSS multiplied by the gain over the PSRR, for instance, VSS or VCC by the plus. Okay? So this is what these expressions are telling us. But instead of looking at this expression, we can write it in another way. So this expression at the output is equivalent to having some noise at the input, let's call it N, which is VSS over PSRR minus. Okay, these two expressions are equivalent. Just because at the output, Vin gets multiplied by the gain. So at the output, we get exactly the same expressions. But this way, we can interpret this noise at the signal, at the power supply, as just some noise which can be added at the input. Okay? Do you understand that? So we are just saying that the noise at the power supply can be reformulated as noise at the input using these two magnitudes, okay, that are quite complex to calculate analytically. Okay? Yeah. For instance, if we wish to interpret, if we wish to amplify one input signal, one millivolt input signal, okay, so if we are working with signals at that 1 millivolt amplitude, and we are having a ripple at the power supply voltage, we need a power supply rejection rate over 40 dBs. Okay, which is over 100 times. Okay? In fact, much higher, because otherwise the signal will overlap. Most probably that would be 80 dBs. Notice that these 40 dBs would imply that this signal, that this signal would be our 1 millivolt signal plus the 100 millivolt over the PSRR, and 40 dBs is just 100. So that would be more or less 1 millivolt signal plus 1 millivolt noise. So in order to get something useful, our PSRR should be probably around higher than 80 dBs in order to get less than 1% of noise. Okay? Yeah? Okay. Then the problem is, how can we integrate in an integrated circuit is that it's very complex to integrate resistors. Okay? They are awfully difficult to implement, and the values are always very complex to get. They are bad. Okay, resistors are bad when you are talking about integrated circuits. So we need to look for other alternatives. The first solution is using, for instance, 2 transistors instead of 2 resistors. Okay, we just get 2 resistors and we put them in this kind of configuration, and they are acting as active resistances, as active resistors. Okay, after that, we repeat the same analysis for the differential gain. Okay, and we just replace. Notice that this transistor, so fashion. Okay, this is the configuration. This is the drain, the source, and the gate. Okay, so in this case, the small signal is this one. This is the gate and the source. Okay, so we are having something like that. And this is GM multiplied by BG. Okay, and you know, let me draw it here, that you are having here, this is just VG, VS, and this is something GM multiplied by VG minus VS. Okay? And notice that this is a resistor. This is equivalent to a resistor with value 1 over GM. Okay? Yes? And then using this, we get to this expression, which is the equivalent, this equivalent resistor in parallel with the output resistor. Okay. Usually, this resistor is much smaller than the output resistance. So what we get finally is that the differential gain is related to the gain of the first transistor, of the input transistor, over the gain of the second transistor, which is frankly not easy to get very high. Okay, it's just the relation between the area, the sizes of these both of these transistors. So remember that the GM is just beta E tail. Okay, so the relation between GM1 and GM3 is the proportion between the transconductances, the betas of the transistors. Okay, so this is the square root of the transistors, of the size of the transistors. So this is difficult to get very big because the size is limited. So the problem is that it's difficult to achieve high gains, which is bad for us because we want for the gain to be as high as possible. So what can we do? Okay, we can use another kind of active load. What kind of active load? Okay, the problem here is this GM, this gain here. Okay, and this gain is caused by the configuration of the transistor having the gate connected to the source. Sorry, the gate connected to the drain. But the only thing we need here is, the only thing we do that is in order for the gate of the transistor to have a given bias point. Okay, we don't need this connection for anything else than getting this bias point. So, okay, let's provide it with a bias which is not dependent on this drain. Okay, if we get a bias not depending on this point, on this voltage, we get a much higher gain because we remove this dependence on the VGS, so this GM3 will disappear. Okay, so in this case, we just replace the transistors, we remove this, and we replace it by a given bias voltage, which is independent on the other voltages. Okay, so we do again the half circuit theorem, and this dependence here has disappeared. Okay, so now we only have the parallel of these two resistances, which is much higher than in the other case, because we have removed this dependence on the gain of the third transistor. Okay, just by adding an external bias, an external voltage which needs to be generated. Okay, so in this case, the potential gain is much higher. But anyway, it can be destroyed by a resistive load. In any case, remember that the gain for a common source amplifier was GM multiplied by the output resistance. Okay? So in this case, notice that we are reducing the gain because we are using this, a parallel of two resistors that can be smaller than this gain. Okay, but in any case, we are having an improvement because we are having a differential input, which is better than having just a single input, a single-ended input. Okay, and in this case, the resistive load is always present. So, but here what we are talking is that if we wish this to be a high gain amplifier, most probably we will need to add something after these outputs, which is not resistive, so that we can keep all the advantages of a differential input and then get more gain at the second stage. Okay, but this is something that needs to be talked more in another lesson. So how can we get this bias? This is the bias. Okay, so we do that by using something which are called current mirrors. Okay, do you remember current mirrors? I think you studied them somewhere, but they didn't tell you that they were very important. Do you remember these current mirrors? It rings a bell. Okay. Okay. Yeah. But current mirrors are probably the second most important circuit or transistor configuration in all analog electronics. And if you belong to a given school of thought, thought. Maybe they are more important even than differential amplifiers. Okay, if you are Swiss, maybe current mirrors are more important than other things. In fact, there are two schools of thought in analog electronics. Okay, one current of thought is the main current, which is the one that nearly everybody follows, which thinks that the most important things are voltages. Okay, I think you are included in that school of thought because nearly everything you have done is based on looking at voltages. Okay, for you, current is just a byproduct of having things, but you always look at the voltage. Okay, till now. And the other school of thought is a very minority school, which is represented mainly by a Swiss guy called Christian or Eric Vitoth. Eric Vitoth is probably the father of this school of thought, and they are using currents instead of voltages. Okay, and using current instead of voltages has some defined advantages. We will not be discussing that now. Okay, but just keep in mind that maybe always using the voltage as your main reference is not a good idea. So from time to time, it's better to go to the current. Okay, but anyway, here a current mirror is just a device that is able to reproduce the current flowing through this branch into this other branch. And in fact, it is reproducing the current here. Notice that these two transistors are sharing the same gate voltage. Okay, VGS 1 equals VGS 2. Okay, and if this is true for this and for this transistor, and if both transistors are the same, VGS 1 minus VT, which is equal to beta VGS 2 minus VT, which is equal to the current flowing through the second transistor. Okay? Yep. So this is why they are called current mirrors. Under certain conditions, the current through one of them is copied into the others. Okay, notice that the current through this one, through the first branch, is copied in this branch, but also in this branch. And in this branch is multiplied by 2. Okay, because this beta is twice. It's 2 beta. And the current flowing through this branch is copied into this branch and into this branch, because they are sharing the same voltage between gate and source. Okay? Yep. So this is the main idea of a current mirror. I think it's quite more complex, as we shall see in the next session. Okay. Any questions till now? Is it okay? No questions? Okay, so if you don't mind, I think we can stop here today. I've got a fever, and for me it's being quite hard. Okay, so I will post this session also on YouTube. I will edit out some of the worst points. Okay, and we meet again on Friday, also here in the virtual class. Okay. Yeah. Oh, thank you. So I'm